you better compute results that are the same as if you ran them in the order that I told you. But if you run them in a different order and I can't tell the difference, then it's okay. And that's a really big difference. This program that I have right here is a sequential program. I have written this program which says the output that I want is as if you did this, and then this, and then this, and then this. I didn't think about parallelism at all when I wrote my program. But I wrote a program where someone can muck with the order, in particular make it parallel, and I'd get the same result. I would never know. But my program would be faster. Right? So like, for example, what if we had 3 processors? Could we do better? Well, before, what did I do? I did it in 3 cycles. If we have 3 processors, how long would it take? Are you sure? Why 3? Well, I can definitely parallelize the first 3 operations all I want, but I have a chain of dependencies that keeps things 3 cycles. Yes, sir?
So doesn't each processor have its own, like, in this example, like, so that
I'm speaking very abstractly right now. Just imagine that, like, we have the ability to execute 3 things at once, and I'll come back to that in 1 second. Good question. Right? So conceptually, when I look at my program, and that instruction sequence that I gave you, actually, I'm just rewriting it now as something that may be a lot more familiar, like a dot product between 2, 3 vectors, key machine learning operation. These are the true dependencies, and this program has different amounts of parallelism at different points. Okay? So this gets to key idea number 1 today, or, well, we've had a few key ideas today, but it gets to the reason why more transistors did translate into more performance, which is processor architects were designing hardware that were looking at the programs that you gave it and said, they didn't do any parallelism, but hey, look what I found. I happen to have multiple instruction units that I can do multiple things at once. I will go find it, and I will reorder the program to be parallel for you without looking, without you ever knowing. And so to your question about registers and stuff, really what I mean here is we've replicated, we still have 1 core, but we have 2 execution units and ability to execute 2 instructions per clock now. And I added this out-of-order control logic box just to say that now there's some smarts in the processor to figure out what's going on. And if we look back like 20 years, you look like for a simple Pentium 4 processor, this is a diagram from a long, long time ago, and I draw my color scheme on it, it's not all that different from my little cartoon. They have the ability to execute up to 4 different instructions at the same time, or 3 instructions at the same time with a variety of units. And real programs are a lot more complex. Here's a longer instruction sequence. A good thing to do on your own is to kind of verify that this is the dependency graph for that instruction stream. And that dependency graph is limiting the total amount of parallelism that you could ever find with this technique of automatically parallelizing within a single processor without you ever knowing it. Yes?
What would we look at where to understand better how that actually happens in the processor?
Well, superscalar execution is the first one, and then you need a good reordering algorithm. You could start with Tomasulo's or something like that. I don't know if these days if that's the best.
Yeah, I mean, basically out-of-order execution is the key.
Yeah, go to Hennessy and Patterson, read the out-of-order execution channel, and then you're well prepared for EE280. But there's a problem. Remember when I said if we had the ability to do 3 things at once, we ended up in the same performance as 2 things at once? That's because if I write just like a sequence of instructions, there kind of usually is fundamentally an order to it, right? And so folks studied, here at Stanford, actually, the early days of parallel computing, they did a lot of studies of how much parallelism could we automatically extract if we asked the programmer to do nothing and we found what parallelism exists in their program. And they found that the x-axis here is the number of operations this processor could do at the same time, and the y-axis is the speed up. And they found that, once you build about 3 or 4 operations at the same time into your processor, if you start building more, you can't use them because programs don't have that parallelism. Okay? So all of a sudden, they could stop. They couldn't play this trick for you anymore to speed things up. Okay. All right, so here's a graph that you probably would have seen. Again, it's x-axis as it's a fancier version of Kuhnle's old graph. Of x-axis is performance. X-axis is time, and the y-axis is actually transistors, not performance. It's transistors per chip. And in general, okay, now we're starting to fall off of it for the last 5 years or so. But in general, we've been able to shrink transistors for pretty reliably for up until very recent times. Like more and more transistors. Like in a modern NVIDIA chip has something like, I think 100 billion transistors on it. I think it's like 85 billion was the last one. So, but we can't turn those transistors into more execution units because we know we can only do about 3 of those things. So that's sort of this green line. This green line is transistors per chip. The purple line here is operations per clock. And they stopped adding operations per clock because it didn't help anymore. Now the dark blue line, correlate, both blue lines are actually, they were increasing clock speed, like 500 megahertz, 750 megahertz, gigahertz, 2 gigahertz, 4 gigahertz. And that's what really stopped moving about 15 years ago, right? And for the architects in the room, do you have an idea why clock frequency stopped? Yep. Because of power, right? So we couldn't turn more transistors into free parallelism, and we couldn't make your instruction stream go faster because we couldn't increase the frequency of the machine, right? And that's completely power driven. Like these processors that you see today are non-trivial. Like if you take an RTX 4090 GPU and you take the microwave in my kitchen, you are within a factor of 2 of running that thing, in a machine learning workload at full tilt versus microwaving your yesterday's hamburger. You are in the same ballpark of energy being spent. And that energy translates into heat. Heat translates into the need to cool that thing. And so you just cannot continue to increase frequency. And we'll talk a little bit more about that. But a nice rule of thumb is that power is going to go as the square of frequency. So x-axis here is clock speed. Y-axis is power consumption. So it's a very inefficient way to go faster is to try and increase that clock. Okay? So this is where we were not so long ago, when I was in grad school. Software, all of a sudden, the only way to use all these transistors would be I, as the programmer, have to tell the processor, here are 2 things we can do at once. Now, luckily, in machine learning and computer graphics and image processing and photography, that's going to be pretty easy. And so that's when people started building processors with chips with a bunch of processors in it, where they took that one single instruction stream and allowed for more and more things to go in parallel. So one of the things you're going to do in this class